All right, so let's get started with this. We are doing the clocks and codes playground. Codes are how computers keep secrets. Codes are also how people keep secrets from computers. What does it really mean when a website is secure and your browser shows a tiny lock symbol by the website name? Why do modern hackers spend most of their time trying to trick people into revealing passwords instead of using code-breaking tricks? Why are governments able to sometimes break each other's codes, but not do so regularly? Cryptography can be fun. Did you ever play with secret codes as a kid? Let's explore the fundamentals of cryptography. The math starts out easy, but at the end gets tricky. Most of the playground will be interesting and fun. If the very end is too hard, it is okay to skip it or get help. We all sometimes play a video game and get stuck on the final boss fight. Part 1. Clocks. 12-hour clock. Begin at the beginning, the king said very gravely, and go on till you come to the end, then stop. Lewis Carroll, Alice in Wonderland. One of my favorite works of literature. Alright, where do we start when talking about codes? We start with a sentence that will not make sense right away, but will soon. Modern codes are based on clocks, as division will be broken. To understand that strange but true sentence, we should start at the beginning. We start with math on a 12-hour clock. Math on a clock wraps around. After 12 o'clock, we go back to the beginning. If we count 5 hours past 11 o'clock, we don't say 16 o'clock, but instead say 4 o'clock. In a sense, 16 o'clock and 4 o'clock are two names for the same thing, but we don't want to say they are equal or write 16 equal 4. That looks wrong and hurts my brain. The official word we use instead of equal is congruent. Instead of equal signs, we use a slightly different congruent symbol. The equation we write is called a congruence and looks like this. 16 congruent to 4 on a 12-hour clock. Similarly, if a 7-hour plane flight from New York to London starts at 6 o'clock, we say it arrives at 1 o'clock instead of 13 o'clock. 13 congruent to 1 on a 12-hour clock. We can add the same amount on both sides of a congruence. This is arithmetic that represents moving the clock hand clockwise. Let's move time ahead 2 hours. 13 plus 2 is congruent to 1 plus 2 on a 12-hour clock. 15 is congruent to 3 on a 12-hour clock. We can subtract the same amount on both sides of a congruence. This is arithmetic that represents moving the clock hand counterclockwise. Let's undo the earlier shift by moving time back 2 hours. 15 minus 2 congruent, 3 minus 2 on 12-hour clock. 13 congruent, 1 on 12-hour clock. Notice that clock arithmetic does have a 0. We just normally call it 12 o'clock. 12 congruent 0 on a 12-hour clock. We can multiply the same amount on both sides of the congruent. What does multiplying mean? 3 o'clock times 4 really means move 3 hours clockwise 4 times starting from 0. Multiplying is repetitive adding, just the way we normally think about it. It represents starting from 0 and moving the clock hand forward repetitively. 15 times 2 congruent, 3 times 2 on a 12-hour clock. 30 congruent, 6 on a 12-hour clock. So far, so good. Division does not work reliably on a clock. Let's try it. 13 divided by 3 congruent, 3 divided by 3 on a 12-hour clock. Does this work? 5 congruent, 1 on a 12-hour clock. Does this work? No. This is not true. 5 o'clock is not congruent to 1 o'clock. How wonderful! Soon we will use arithmetic to make a code. I want a process that is easy to do. We want a process that is easy to do but hard to undo, so our code is not easily broken. With normal arithmetic, that is impossible. If we do something with addition, we can undo it with subtraction. Or if we do something with multiplication, we can undo it with division. But when using clock math, division does not work. With clock math, doing something with multiplication can be hard to undo. If this was a video game, we are still in the tutorial, but we have picked up our first weapon. Yeah, a 24-hour clock. It's then we'll hear St. Peter tell us loudly with a yell, "Take a front seat, you soldiermen. You've done your hitch in hell." Frank Bernard Camp, our hitch in hell. What if our clock used military time? Now the clock has 24 hours instead of 12. It is no longer true that 16 and 4 are congruent because in military time, 1600 and 0400 are two different things. If a 7-hour plane flight to New York and London starts at 1800, it goes past midnight to 0100. 25 congruent to 1 on a 24-hour clock. Unfortunately, looking at military time was only a tangent. We will build off this idea. If this was a video game, we're still in the tutorial, and we're caught in melee attack we will never use again. You turn to flex your cryptography muscles. Check for yourself that addition, subtraction, multiplication still work on a 24-hour clock. What value is equivalent to 0 on a 24-hour clock? I would say 24-hour is congruent to 0 on a 24-hour clock. As for checking to see if addition, subtraction, multiplication still work on a 24-hour clock, let's use this one as a base. 25 congruent to 1. So 25 plus 5 would be 30. 1 plus 5 would be 6. No, I would not think that would be the same. Well, possibly. Subtraction 30 minus 5 is 25. 6 minus 5 is 1. So theoretically it would work because 30 hours is congruent to 6 hours on a 24-hour clock. So in that sense, yes, addition, subtraction, and multiplication would still work. Let's see here. Let's again use the 25 congruent to 1. So 25 times 2 is 50, and 1 times 2 is 2. I would not think that that would be congruent with each other. Yeah, I would not think that would be concurrent. So, I don't know. I do not know the answer to this, but I'm learning that it is a lot easier to do work on a 12-hour clock rather than a 24-hour clock. So most likely won't ever use the 24-hour clock unless specifically working with military time. So, yeah. A 26-letter cipher. Okay, so the entire alphabet is 26 letters. A, B, C, A, B, C, D, E, F, G, H, I, J, K, L, M, N, Q, R, S, T, U. Yep, the entire alphabet is 26 letters. How long do I want these messages to remain secret? I want them to remain secret for as long as men are capable of evil. Neil Stephenson, Cryptonomicon. That's pretty cool. To start making codes, we introduce the traditional way of making numbers and letters correspond. This way to make back and forth from letters to numbers is called a cipher. In theory, we could use a cipher that was not so obvious with all the numbers in order, but we use this most natural cipher and let the math we do to the cipher make our code secure. In the cipher, we write first the numbers as 01 through 09. Eventually, it will be convenient for every number of the cipher to be two digits. Notice that the letter Z could be represented by either 0 or 26. This, just like on a 12-hour clock, 12 o'clock behaves like 0. 0 concurrent 26 on a 26-letter cipher. In a moment, we will plug these numbers into formulas. What happens if the answer is bigger than 26? We wrap around just like the clock math clock. Okay. The directions about how to wrap around must be included in each congruence. Those phrases are getting a bit longer. We do not want to write on our 26-letter cipher again and again. So mathematicians use the jargon mod to describe when to wrap around. It does not really matter whether the real-life application is a clock or a cipher. 16 concurrent 4 mod 12 on a 12-hour clock, both represents 4 o'clock. 25 concurrent 1 mod 24. 31 concurrent 5 mod 26. The word mod is an abbreviation of modulo. Modulo? The more official name for clock math is modulo arithmetic. I have no clue if I'm pronouncing that correctly, but I really do not care. Now we are making progress. We want to make codes out of words, not times. If this was a video game, we are almost done with the tutorial and have to just pick up the ammunition of our weapon. Okay. Part 2, codes. Do the Caesar shift. The die is cast. Julius Caesar. The most natural thing to do to a clock is shift forward or back a few hours. So our first type of code will merely involve shifting between letters back and forth in exactly the same way. This works great early in the alphabet. If we shift 8 spots to the right, then A becomes I, B becomes G, and so on. But what do we do with V? If we try to shift V 8 spots to the right, we could fall off the end of the alphabet. So we wrap around, of course. We are used to that by now. Historians know that Julius Caesar used this type of code. Let's use his famous sentence, "The die is cast," in our example. I like that sentence because I'm lazy, and all his other famous sentences are much longer. We use our cipher to change our messaging. 20, 08, 05, 04, 09, 05, 09, 19, 03, 01, 19, 20. When we disguise each number by shifting it to the right 8 spots and wrapping around is needed just to establish good habits. We will take a moment to write this successfully in an encryption formula. Disguise congruent number plus 8, mod 26. Here are the shifted numbers: 02, 16, 13, 12, 17, 13. 17, 01, 11, 09, 01, 02. For most codes, we stop here and send those disguised numbers as the code. But to follow historical tradition, when doing the Caesar shift, we use the cipher a second time to translate back into letters and send those as our code. BPM, LTM, QA, KIAB. Ta-da! That was easy. Obviously, the recipient should use a decryption formula that shifts each number by -8 and wrapping around as needed. Number congruent disguise -8 mod 26. Perhaps you played with this type of code as a child. You probably saw it as easy to break code. Some letters appear much more frequently on average. Overall, E appears as 13% of the letters in a sentence. T is 9%. I, N, and R are 8%. A and O are 7%. Furthermore, certain words are much more common. The top 15 appearing words are the, be, to, of, and a in that, have I, it for not, on which. No, which, with. With. Not sure where I got which, but it's with. Because the encryption formula is applied to one letter at a time, those hints about letter and word frequency make breaking the code much easier. Even in our encryption formula was thicker than add 8, this style of code is still easy to break. If this was a video game, we have finished the tutorial. The game begins. We have no power-ups yet and are really wimpy. You turn to flex your cryptographic muscles, use the Caesar shift page at crypty.com to make a Caesar shift code message. Give it to someone else to solve if you are nice. Also share the facts about the most common letters and words. Hint, don't be nice. I'm going to choose not to do that, just because it's me. Alright. Have a block party. Spending time with math people is a lot of fun. As a result of the play, I had semi-drunken dinners with mathematicians all over the country, I recommend the experience. David Alburn, playwright of Proof. To make a better code, we smooth together the numbers made with the cipher into blocks. We will be wimpy to use blocks made with only 2 letters, even though short blocks make a much more secure code. The die is cast 20, 08, 05, 04, 09, 05, 09, 019, 03, 01, 19, 20, 02, 16, 13, 12, 17, 13, 17, 01, 11, 09, 01, 02. BP, ML, TM, QA, KI, AB. This makes slightly more work for the recipient. He or she now receives a message without the spaces between words. The decoded message is now THEDIEISCAST. Fortunately, it is usually easy to see where the spaces should be to make real words and a sensible sentence. In theory, we can make our cipher bigger so it includes punctuation, but we're too lazy. But we're not done yet. As long as we are smoothing together pairs of numbers, why don't we treat each pair a single 4-digit number? The die is cast 2008, 0504, 0905, 0919, 0301, 1920. That allows us to use a more complicated encryption formula. Disguise concurrent number times 6 mod 26. The resulting code becomes 12048, 3024, 5430, 5514, 1806, 11520. Now we're getting somewhere. The blocks prevent a code breaker from using hints about letters and word frequency. This is finally a code that the average third grader cannot break. The recipient will need to use the opposite formula to decrypt the message. Number concurrent disguise divided by 6 mod 26. As before, the decoded message will be THEDIEISCAST. And the recipient will need to fix the spaces to make a sensible sentence. The previous code required the recipient to know the key for the code, which was divide by 6. But how does the recipient get the key in the first place? Our codes provide no secrecy. If the sender's first message must be uncoded and include the key used in later coded messages. An eavesdropper could intercept the first message and steal the key. Our codes are pitifully inefficient if the sender and recipient must meet face-to-face to exchange the key. If this was a video game, we have found the first quest. You turn to flex your cryptographic muscles. Visit the Practical Cryptography website to read about the classical encoding plan other than the Caesar shift. Part 3, Key Exchange Quest. A court order is as ineffective as accessing encrypted data as a nuclear weapon. Only the key holder can access that data, and that power resides exclusively with them. Jacob Riggs. Our quest again involves modulo arithmetic. It will help to watch this video about end-to-end encryption that makes the issue clear.
So recently, the Home Secretary of the United Kingdom government was at Brexit new.
So I just went ahead and I watched the two videos. I paused the recording and I went and I watched them. They're really good with information, right? And this video introduces how secret sharing a key involves mixing three things. So it talks about that, right? Those videos avoid the nitty-gritty, but we are all up for the challenge. Imagine that Alice and Bob, which are the characters that this guy right here in this thumbnail created, want to create a key without sharing the key with an eavesdropper named Eve, which is another character that he came up with. Alice and Bob begin by sharing publicly that they will use a congruence with an exponent. Y equals 11, secret mod 26. Alice picks 5 for her secret exponent. She plugs it in and sees that 7 congruent 11 to the 5th power mod 26. So she sends to Bob the number 7. Bob picks 14 for his secret exponent. He plugs it and sees that 17 congruent 11 to the 14th power mod 26. So he sends to Alice the number 17. So far, Eve has seen which style of congruence they are using in the numbers 7 and 17. But division does not work reliably with modulo arithmetic. So Eve cannot work backwards to find the secret exponents. Next, Alice changes her congruence to have Bob's number as the base of the exponent, with her own secret number as the top exponent. She sees that 23 congruent 17 to the 5th power, mod 26. Similarly, Bob changes his congruence to have Alice's number as the base of the exponents, with his own secret number as the top of the exponent. He sees that 23 congruent 7 to the 14th power, mod 26. Ta-da! Alice and Bob now both have the same number of 23 to use as a key. Eve cannot combine her information to get 23. A modern key exchange would use a more complicated formula and bigger numbers, but the essence remains the same. Being able to create a secret code is amazing. It also does not take very long with a computer. In a spreadsheet, you can type equal mod 7, 14 and get these kinds of answers instantly. When your smartphone sends a text message, it does this type of thing with every single text message. The messages are more secure and the software is constantly creating new keys. If this was a video game, we have finished the first quest. The reward was a power-up that made us grown stronger. We are ready for the boss fight. Yeah, it's a really short video game. I would say that is a very, very short video game. Part 4, Modern Codes. On 2 occasions, I have been asked by members of Parliament, pray, Mr. Babbage, if you put into a machine wrong figures, will the right answers come out? I am not able to rightly apprehend the kind of confusion of ideas that could provoke such a question. Charles Babbage. Our ability to secretly create and share key is amazing, but our encryption and decryption formulas were too wimpy. Merely dividing by a number is not a strong enough encryption formula. The history of better encryption formulas is tied to the history of computers. The hunt for the best encryption formula is like Goldilocks in the House of the Three Bears. We want it to be just right, instead of too simple or too complicated. If the formula is too simple, then a code breaker can break the code. If the formula is too complicated, then it takes too long to send and receive a code. The most famous mathematicians studying codes during World War II were Elizabeth and William Friedman. They knew that the supercomputers of their time would eventually be able to break any code, but they discovered encryption formulas that would make Goldilocks happy. A message could be sent in seconds, but breaking the code could take years. Since the 1970s, the common encryption formula has the same appearance as the key exchange formula, a concurrence with an exponent. The sender plugs one block at a time into the bottom of the exponent, making the top of the exponent bigger. As computers get faster, keeps Goldilocks happy. In our example of a key exchange, we use a concurrence and wrapped around at 26. Our new encryption formula needs to avoid dissecting our biggest possible block, which is YY, or 2525. So we will work with a number bigger than that. Let's use 2633 to keep the 26-ish vibe. Encryption equals block, exponent key, mod 2633. Encoding a modern code. Perl is the only programming language that looks the same before and after encryption. Keith Bostick. Here we go. As before, we use our cipher to make pairs of letters with 4-digit blocks. The die is cast 2008, 0504, 0905, 0919, 0301, 1920. For example, let's start with the smaller number as the top of the exponent. Let's use 3. Encryption, concurrent block 3. When we cube each of our 4-digit blocks, we get big numbers. 8096384512, 128024064, 741217, 776151559, 27270 7077 888 Next, we wrap around on an imaginary clock with 2,633 hours. This is trivial with computer help. in a spreadsheet, you can type equal mod 809638451 comma 2633 to instantly get the first block's answer of 1667. Modulo arithmetic calculator at Planet Calc can also find 809638451 modulo 2633. The code we send ends up being these 6 blocks: 1667, 2338, 1795, 1085, 0920, 2215. So far, so good. Decoding the modern code. Unbelievable. You, subject name here, must be the pride of subject hometown. Here. GLaDOS. How does the recipient decode the message? The corresponding decryption formula is disguise concurrent number 1755. Do you not know where the 1755 came from? Trust me, that it is advanced math, but quick math. Our code's recipient must plug in the 6 blocks one at a time. The first block is block concurrent 1667, 1755, mod 2633. Uh-oh, boss fight. Can we figure out 1667, 1755? That is a disgustingly big number. Our calculators cannot handle it. Our spreadsheets cannot handle it. The fact that we are doing modulo arithmetic saves the day. Not only does modulo arithmetic break division, so Eve cannot eavesdrop on the key exchange, but it gives us a backdoor into math problems with disgustingly big numbers. If this was a video game, we ready our weapons and ammunition. We approach 1667, 1755. It towers above us. We cannot see it clearly, fortunately. We do not need to know this number. This Grimm's number is 1667 times 1667 times 1667 times 1667 times, with the multiplication happening for 1755 repetitions. If this was a video game in the cave with the boss fight, it's a skeleton, an adventurer who tried to fight the boss and failed. What did he do wrong? He started the chain of multiplying. He died. 1667 times 1667 equals 2,778,889, which wraps around and becomes 1,074. Mod 2633. And then he could multiply by the third 1667 and again use the mod 2633 purportedly to shrink the number down to a reasonable number, and so on. But before he finished all 1754 steps, he died of boredom. Perhaps you have seen the product rule of exponents. 1667a plus b equals 1667a times 1667b. So 1667 1755 equals 1667 1 plus 2 plus 8 plus 16 plus 64 plus 128 plus 512 plus 1024 equals 1665 1 times 1667 2 times 1667 8 times 1667 16 times 1667 64 times 1667 528 times 1667, 512 times 1667, 1024. We can use the congruences with the 8 smaller exponents without too much spreadsheet work because of a pattern. 1667 1 equals 1667. Because of this is less than 263 3. It does not wrap around. 1667 2 equals 2,778,889 equals 1,074 mod 2633. 1667 4 equals 1667 2 times 1667 2, but from what we just did, this is the equivalent to 1074 times 1074, 1,153,400, 1,153,476. Then we find 1,153,476 congruent to 22 mod 2633. 1667 8 equals 1667 4 times 1667 4, but from what we just did, the equivalent to 222 times 222 equals 49,248. When we find 49,284, congruent 1890 mod 2633. 1667 16 equal 1667 8 times 1667 8. From what we just did, this is equivalent to 1890 times 1890 equal 3,572,100. Then we find 3,572,100 congruent 1752 mod 2633, and so on, because letting the exponents double keeps the pattern going. To get to 1667 1024, we follow this pattern 11 times. If this was a video game, our ammunition has been used 11 times, our weapon is warm. We still end up with really big product of 8 numbers: 1667, 1755, 1667 times 1074 times 1890 times 1752 times 351 times 2083 times 160 times 64. The modulo arithmetic again makes this manageable. With the product of only 8 parts instead of 1755, we can behave like the skeletonized adventurer and approach the long bunch of multiplication, one product at a time without dying of boredom. We start with the first 2 numbers of our product. We multiply 1667 by 1074 equals 1,790,358. Then we find 1,790,358 equal congruent to 2551 mod 2633. To keep going, we need to also multiply by 1890. We multiply 2551 times 1890 equals 4,821,390. We find that 4,821,390 congruent 367 mod 2633. To keep going, we need to also multiply by 1752. We multiply 367 times 1752 equals 642.9840. We also find that 642.9840 congruent 532 mod 2633, and so on. Eventually, we get to the last step where we include the times 65. The result of the previous step was 598. So 598 times 65 equals 38,870, which is the concurrent of 2008, which was indeed our first 4-digit block representing the letters TH. If this was a video game, our ammunition had been used 7 more times, our weapon is hot, but 1 block is decoded. The battle continues until all 6 blocks are decoded. The recipient reads THEDIEISCAST, and the boss is defeated. Whew, that was a fair amount of math for just 1 block, even using a spreadsheet to do the modulo arithmetic instantly, but we need enough complication to make the code unbreakable. If our example above, the encryption and decryption formula, had exponents whose top numbers were 3 and 1755, the second was the key, so our code that the recipient needed to know to decode the message, it was a pretty big number in the thousands. Back in the days of Elizabeth and William Friedman, during World War II, a key in the thousands would have been sufficient. The biggest computer of the era, like the Colossus, could not break that kind of code before the relevant battle was to be over and the information was obsolete. Remember, the exponent style of encryption and decryption formulas were not actually used until the 1970s. We are just making a comment about supercomputer speed. Today, much bigger exponent keys are needed for security, making the exponent have an additional 3 digits from thousands to millions, about doubles the time needed to use the code and the time needed to break the code. We can keep repeating this, changing the key from a number in the millions to a number in the billions again doubles the time. And changing the key from the number in the billions to the number in the trillions again doubles the time. Since 1980, supercomputers have become so fast that they can break the code with an 80-digit exponent key in less than a day. Almost a day for a CDC Cyber 205, a few hours for a CRAY-XMP, as documented here. In 1980, CRAY-XMP, that's how I'm deciding to say that, has a speed of 0.8 gigaflops. The current top supercomputers have speeds in the millions of gigaflops. I have no idea what that really means, but it is fun to say. That indeed it is, David. It is indeed super fun to say gigaflops. Modern encryption and decryption formulas use exponent keys with lots of digits. They generate new keys with every text message and every time a secure website sends or receives information. But the math is still based on the same procedures. Now, to recap, what we have learned in this playground is that codes are very difficult to understand and a lot goes into them, but at the same time, they are a lot of fun. And the more basic ones you can easily figure out if you can figure out how a clock works. Essentially, that is what I have come to understand it as, and it all made a lot more sense. Yes, it takes a lot of math, but if you really like math, it could be a whole lot of fun and a great way to spend your free time. Just decoding something that a friend sent you, just in your free time, no matter how long it might take, a couple centuries, maybe more, not really sure, it depends on how tricky it is. Though if it's between two friends it's very unlikely that it will be a very, very high amount of exponents for what we have just learned. Probably keep it very simple, pretty easy to decode if it's just between two friends, unless they're talking about something really sneaky, like world domination. But most people don't talk about world domination, so I think we're good there. But yeah, that is essentially what this playground is, and I literally just explained my thoughts on it. So, yeah, until the next playground.